Good morning, everyone. Thank you very much for joining today's webinar. Welcome, everybody. So we're going to get started today's webinar. Slowly, people are still joining the room right now. So thank you for joining our first 2026 webinar. Today, we are receiving Professor Haas Webinar. For those who doesn't know the Light Communication Alliance, I will start with a short brief on the Light Communication Alliance. We are a non-profit organization dedicated to educate, disseminate, and work around optical wireless communication technologies. We are working on several different topics, such as normalization, certification, education, standardization around optical wireless communications. We will have several different webinars during the year. You will all receive information about these coming webinars. But today's webinar is about Professor Haas, and I will explain and make a short introduction about the professor. Professor Haas received his PhD from the University of Edinburgh, UK in 2001. He is the Van Eyck Professor of Engineering at the University of Cambridge, where he leads the Li-Fi Research and Development Centre. He is the director of the National UK Future Connectivity Hub on the Networks of Networks, Titan, and co-director of the UK Federated Telecom Hubs. He co-founded Pure Li-Fi and is a member of the board. His research spans from photonics, communication theory, and signal processing to advanced optical wireless communication. He has co-authored over 800 journals and conference papers, with more than 69,000 citations, Google Scholar, and holds over 50 patents. His 2 TED Talks and 1 TEDx talk have attracted over 5.7 million views. His honors include the Royal Society Wolfson Research Merit Award, the IEEE VTS James Evans Avant-Garde Award, and the Hubble Research Award. Professor Haas is an ambassador of Friedrich Alexander University Erfgen-Nürnberg, and he is fellow of the REING, the RSE, the IEEE, and the EIT. And we are very honored today to be able to receive Professor Haas, and we will now give him the floor to give us a talk on the latest recent advance in light-based wireless networking. Professor Haas, the floor is yours. I gave you the lead. Thank you, Professor.
Thank you, Mark, for the kind introduction, and welcome and good morning, everyone who joined today. Let me share my slides, and I hope you can see them. Can you see the slides, and can you hear me well, everyone?
Yes, Professor, this is perfect. Thank you very much.
Good.
Professor, how long do you think you need to do your presentation?
It depends how long you want me to talk, but I was planning 40 minutes or so, that we also have time, hopefully, for a number of good questions and a discussion, or maybe I finish in half an hour, if that makes sense.
That's perfect. Thank you very much. For everybody who is in the chat and actually wants to ask some question, the chat is
Yes,
available,
please.
and you can please share your question, and we'll answer that at the end.
It would be very nice to have a very nice interactive discussion. I think I see a lot of experts on the call here. It would be really great to advance and further the discussions on optical wireless communications. Yes, that would be great.
Thank you very much, Professor. The floor is yours.
Right. Okay. Then let me start. So I'm giving a kind of an overview talk about, sort of in a snapshot way, what we have done in the last few couple of years in terms of optical wireless communications, and yeah, and as I said, hopefully we have a good discussion. So first of all, optical wireless communications, as we know, is a broad term. It covers a lot of things, and it covers a lot of use cases. And the really emerging use cases that I see are fourfold, and you see that on that diagram here. Starlink have shown us that they are advanced on inter-satellite communications with optical terminals. That's in place already. So you see a deployment. You see the likes of Tara that are advancing very quickly on the terrestrial point-to-point free space optical links. We see various activities on underwater subsea communications with light, which is becoming quite an emergent and interesting application space as well, not only for defense, but also deep sea exploration. And then the classic sort of indoor light networking with networking with light. We coined that in Li-Fi, where the idea is, as illustrated there, is you build little small cells within a room that cover a certain area, and then you have a double effect. You have a strong frequency reuse possibility. You see in a room, you have three cells spatially distributed, and at the same time use free spectrum from the light sources. That's the idea of Li-Fi. So these are the four major use cases, and we've summarized it in a paper if you're interested in the Vehicular Technology magazine. So, I mean, I get a lot of questions around Li-Fi and saying, yeah, it's been around for so long. Why do we not see it in our homes? Why is it not widely spread? There's a number of reasons for this, but there's also a reason of technology maturity and scaling in business models and economies of scale, as the RF, as I tried to explain on that slide here, is basically 60 or to 80 years ahead of optical wireless, and that is, I mean, it's manifested itself in yeah, very cost effective sort of silicon that's been developed for radio technologies. The major problem with Li-Fi is that there is no real baseband processing, miniaturized, small chip scale processing technology that takes into account the advantages of light as a bearer of information in free space. So, I mean, you see this, the Bell Labs, sort of Bell's demonstrations of the photophone was 1880. And we had the Marconi's sort of RF transmission over the Atlantic 91, and only in 1979, Keller and Pabst and IBM research really they started the area of wireless networking with light in that infrared. At that time, I mean, RF was already part of cellular systems, and sort of in terms of transmitters, Holonyak sort of LEDs in the 64. This is where sort of the optical domain and the laser, then later 64. This is where optical really started, and again, as I said, 60 to 80 years behind RF. And that is what I guess the curve we are seeing now with a strong, as I showed with the previous slide, uptake of optical wireless communications. And why it's still out and still important to consider is because we are now really advancing into 6G and into sort of the interconnected autonomous systems. I mean, Morgan Stanley forecasts 1 billion humanoid robots by 2050, and we talk about the low altitude economy in Asia primarily. We talk about the driverless cars, the robots. I mean, you have it in homes, you have it outdoors, and that is a number of additional sort of transmitters, receivers, and use cases that need to be supplied with data. So there's also, if you look at applications on the smartphone and these TV screens in general, there is the trend to go to holographic displays. And if you want to have a real life updates with low latency holographic displays, you talk about data rates that are not being able to deliver with radio comms these days. You talk about terabit per second requirements. And even if you use compression techniques, they are still very, very high. And if you want to achieve 1 terabit per second, even at a spectral efficiency of 10 bits per second per hertz, you talk about bandwidth of 10 gigahertz, and that is a third of the RF spectrum. So really, if you want to move into that territory, you have to get to optical. I mean, there's no way around it. And the terabit per second KPI, we've lost a little bit sort of the focus on KPIs and 6G going forward for commercial reasons, primarily linked to MNOs. But the research and the innovations really have that sort of KPI still on the radar. And here's a slide shown by primarily Gerd Fettweis in his talks, which shows the data rate sort of history of the various Wi-Fi standards and 3GPP, where at the moment on paper there are discussions about 10 gigabit per second in Wi-Fi 6 and 1 gigabit per second in 3GPP. But forecasting forward to 35, the goalpost really is a terabit per second in RF as well. And this is where the research is driven. So really corroborating what the high speed needs. So yeah, again, coming back to the spectrum then, you've seen that slide probably many times. You see that squeeze of bandwidth in IEEE Wi-Fi 7, where there is now 4K QAM, and 4K QAM, to realize that everybody who's technically minded here realizes that this is really hard to achieve and maybe only workable for very small distances. Whereas in the optics we still have if that large amount of unused, unregulated spectrum that can be exploited. So the question then really is, terahertz is obviously another option to look at how to exploit unused bandwidth. But terahertz still has the problem of the power gap in the region between 100 gigahertz and 10 terahertz. And if we look at the use cases as we showed before, there's also the problem with atmospheric attenuation using in the sub-terahertz and terahertz spectrum, as shown in the diagram here. You talk about attenuations in the region of 1 dB to 100 dB per kilometer. But if you then go further up into the visible light infrared, you basically drop to 0.1 dB per kilometer. So that's why infrared and visible light, in fact, as well, are very good candidates for outdoor terrestrial transmission systems. So, two reasons to look into optics is the power advantage and as well the attenuation advantage. So what I wanted to show here is traffic forecast is always a difficult thing, and we always said that there is some exponential growth of data traffic, data volume, and about 9 years ago, 2017, we started to build a model where we went back to the Cisco forecasts. There's been sort of traffic forecasts starting 2011 to 2016. They're always 5-year periods where Cisco forecasts the traffic. We have looked at all the forecasts through all these years, and also have then 2019 compared that with the actual traffic at that time, and build our own traffic forecast models going forward, which you see with the red dashed graph. It's the progressive model we've developed, 2019, and the green one is more the conservative model in terms of data traffic forecast. And it's good if you do some research about 10 years ago. It's now 10 years later. It would be sort of prudent to see how well did we do in our forecasts sort of 9 years ago. And so first, before I do that, 2035, the more sort of conservative model said we need about 25 times more bandwidth, and the progressive one is about 100 times more bandwidth required in order to provide the traffic, support the traffic that's generated. So we are now at 26, and we're looking at the Ericsson sort of report. They said 200 exabytes per month is what is currently transmitted through networks, and you see the red dot here. It sits on the lines, but you could argue the variation is not very large. But at least the prediction 10 years ago wasn't too bad, and up until now. Now the real question is what happens in 4 years' time from now. Do we see the traffic moving sort of between the red and the green line? In what way? Do we follow the conservative model or the progressive model? That remains to be seen. But the fact is that we see still a tremendous growth of mobile data traffic. In 2022, as shown here in the zoomed out version, we talked about 60 exabytes per month, and we are now at 200. So it's a factor for almost that we saw an increase in that period. On the other hand, the spectral efficiency in terms of bits per second per hertz of radio doesn't sort of run at the same rate. So that really brings that squeeze that been recognized with Wi-Fi 7, as I showed earlier. People try to squeeze more bits into 1 hertz, and it's not power healthy, and it's not performance healthy in terms of coverage. So now looking at the optical domain, we have that tremendous amount of additional spectrum, but it doesn't mean that we can use it to its full extent. Because if you looked at the required optical electrical conversion is always the problem. I think I'm looking forward to a world where we don't need to go back to the electrical domain where everything is all optical, because that conversion slows down the bandwidth that we can actually exploit. And shown here with that sort of a simple equation, saying if you look at sort of 500 nanometer sort of wavelengths, center wavelengths, you have a spectral emission of 0.4 nanometer, which is very narrow. Then you would need an electrical bandwidth of about 480 gigahertz in order to basically make full use of the available bandwidth in the electrical domain. It's easier when you go to 1500 nanometer, as shown here as well. With 0.4 nanometer, you only need 53 gigahertz electrical bandwidth, and that's exactly where the fiber world sits. And it's maybe you see a good match. But if you go into the visible light, you talk about completely different devices that are needed. And not only the transmitter, primarily the bottleneck is at the receiver these days. But having recognized the bandwidth limitations, we are not only limited to exploiting the bandwidth, we have more degrees of freedom. We have the color domain, wavelength division multiplexing. We have the MIMO, the spatial multiplexing MIMO gain. And we have the topological charge, so the structured light in terms of, for example, OEMs, an additional degree of freedom that can be exploited in order to increase the capacity. And these are all pre-log factors, all in a very, very beneficial region of the equation of Shannon. So now we looked very much, and as others have done as well, into how we can maximize the electrical bandwidth that is just remaining to us, given the suboptimal optical electrical converters such as photodiodes and LEDs and lasers. So 10 years ago, roughly, we did some work with the Institute of Photonics at the University of Strathclyde, Martin Dawson's group, looking at these tiny micro LEDs that came into the world of displays. They're really tiny, and they are typically in an array as a matrix, and they provide optical output powers in the region of 5 milliwatt. And the bandwidth typically is about 60 megahertz, and you see the transfer function on one of the graphs here. But the skew rate of the transfer function is very sort of benign, and that's why you can modulate it far beyond the 3 dB bandwidth with bit and power loading, in addition to DC-00 of DM. And you see on the black staircase, you see the modulation order, the QAM order, going from 8 256 QAM down to PPSK essentially. And if you do, then also adjust the power in the subcarrier, so to maximize the SNR per subcarrier, we ended up in a data rate of about 3 gigabit per second in the below FSC regime with the micro LED. So that was at that time quite, I think, one of the highest results that were reported with micro LEDs. So fast forward now 10 years. So we moved away, and as others have done as well, into looking the infrared spectrum, and in particular VCSELs, vertical cavity surface emitting lasers. These are commodity devices. They are in all your smartphones for face recognition, and the major benefit of VCSELs that we see is that they are not edge emitting, they are sort of surface emitting. So that means you can put them into arrays as you could do micro LEDs as well. So in a collaboration with VI Systems in Germany, they produce VCSELs. We've done a test recently using one of their single mode VCSELs over a distance of 25 centimeter and a fiber coupled receiver in order, as I said, receivers are always the issue. Now we plotted here the same SNR over frequency. You see we go up with healthy SNRs up to 10 gigahertz frequency. That the reason why you see the sharp drop off, the bandwidth of this oscilloscope was 10 gigahertz. So that's why we had a drop off. But with that sort of kind of electrical bandwidth that's available with VCSELs and bit and power loading and OFDM, we could drive that to close to 70 gigabit per second. So this is a factor of 10 to 20 higher than the micro LEDs 10 years ago. So you see, we are, and even with sort of, in this case, IMDD systems moving into the upper hundreds of gigabits per second with fairly sort of straightforward, simple systems. I talked early on in the equation, I just put that here to remember that parameter L, the topological charge, the helix structure of a light wave that in itself then offers the opportunity for orthogonal modes, typically inform as various donut shapes, which is one of the disadvantage, by the way, that the energy is concentrated around the center. So nonetheless, so if we looked at sort of 4 orthogonal OEM modes, L1 to L4, and in conjunction with a 1300 nanometer VCSEL is another area we are trying to push. And at the moment, there's no real high power commercial 1300 nanometer VCSELs available, but the industry is moving into that direction. And the reason we are looking at that wavelength is for eye safety reasons, because you have much more relaxed power requirements in that wavelength domain, 3O band. So we've taken the different modes, as you see here, L1 to L4, and they are orthogonal. They're on top of each other. And then if you demultiplex with spatial light modulators or meta surfaces at the receiver, you can then, you have a parallel number of streams. And in this case here, we showed 15 gigabit per stream, and the accumulated aggregated data rate, again, was in the region of 35 gigabit per second with much lower frequency bandwidth available. So you can see the trade-off between the various prelock factors in the equation before. So OEMs are studied by Vilna and others extensively over the years, are another powerful instrument in order to enhance data rates. But some of the work we did recently is that they are really require strong alignment and good alignment. Otherwise, you have crosstalk across the modes. So we're working at the moment on ways to mitigate the requirement for alignment to make OEMs also an opportunity, a possibility for indoor, so mobile networking where you don't guarantee alignment all the time. So one of the motivation and one of the use cases that we see is, well, if you look at the scalability of data center and centers and the micro data centers, they're always limited by the number of connections, the wired connections, so Ethernet cables. So the idea is to pick up sort of one of the thought in sort of acknowledging that we don't have bespoke basebands for light communication. So why don't we exploit existing basebands? And the Ethernet is a well-established baseband with a fairly low chip cost. And at the same time, we can mitigate and remove the cable. So we built an Ethernet link with an optical wireless link. So the idea really is being you take the Ethernet or the 8 channels and then have a media converter and an SFP, get a single output, send it to a VCSEL, a pin diode. Then the SFP board converts it back into the electrical domain with a media converter back into the Ethernet channel, and that is both directions. You see the experiment here with the 2 links. You see the media server. Sorry, get my pointer here. Here's a media server, here's the laptop, and you get the SFPs and the electrical sort of signals going out, and they're going to the 2 links, 1 meter link, and have a bidirectional full duplex communication link. There's no signal processing in between. It's a direct signal that's coming out of the media converter, and the eye diagram is shown here. Quality factor of 7, so fairly good for BR at 10 to the power of minus 13. So there's no intermediate signal processing needed. It's a 1 gigabit Ethernet cable. We get about 800 to 900 megabit up and download. The advantage here really is that because there's no intermediate signal processing, the latency is literally limited by propagation delay and some internal sort of processing to about 25 nanoseconds. So 25 nanosecond low latency optical wireless link is something we demonstrated here. But then the question is, again, how well can you be, or how robust can you be with to misalignment? So we did some misalignment tests with that link. So within a sort of a lateral distance of around 1 centimeter, you still got the quality at a level that you could decode at the required bit error performances. So fairly robust to misalignment. So it may be a good way to replace wired links with an optical link using, as I said here, bespoke Ethernet basebands. So looking now into more the outdoor use cases, and there's quite some impressive demonstrations that have been done. So the ETH in Switzerland have recently shown a terabit per second link over 50 kilometer, as you've seen here. There's others that have shown terabit per second links with wavelength division multiplexing, something I haven't alluded to or not shown yet, but using different wavelengths, you could demonstrate similar data rates. So that is shown. And a very prospective sort of area of development. The problem really in FSO outdoor is on the beam acquisition and tracking. There's also some work that the Institute of Photonics in Strathclyde and with collaboration with us have done in trying to find good ways of connecting outdoors and getting rid of shot noise effects. So working in the solar blind region. So it's the spectrum where the sun doesn't radiate, and that's in the deep UV region between 200 and 250 nanometer. If you look at the spectrum radiation of sun, this is where sun isn't irradiating. So that's why what we looked here is can we use UV for outdoor communication link, which allows us that robustness, as I said earlier, but also allows us to look at communication around corners with exploiting the Rayleigh scattering effect in that wavelength domain. And some work here with an indoor sort of test range showed above 1 gigabit at 100 meters. So that's the 100 meters is primarily power limited, but that's another very interesting area of research looking at UV outdoor communications. Then in Cambridge recently, we've started to do some outdoor FSO tests using gallium nitride lasers, as you see with this link here. This is the motivation really is to look at channel effects in the visible domain outdoors. And the other range of questions we have is how much can we simplify beam acquisition and tracking with an IMDD system? What data rates can we get with optimized modulation techniques? And the third question is how does MIMO work outdoors with IMDD? So we've started gradually moving into answering these questions. So this is a recent published work. Submitted work on such a link. You see, this is the building here at the bottom is the Cambridge Library. This here, that location is our sort of lab location, West Campus in Cambridge. Is a 1.2 kilometer link. So this is the tower. Here is the library in Cambridge, and this is the top of our building. And you see the visible the blue laser link. You see at the receiver side, we have a simple lens, a silicon APD, and with adaptive beat and power loading, that got us to around 6 gigabit per second. And some unpublished work is shown recently with 10 gigabit per second with a MIMO configuration. So that's promising for sort of the outdoor fixed wireless access solutions. And that this system doesn't have any beam acquisition and tracking, really allows very simple alignment. Some additional work and direction we see very promising is to use solar cells as outdoor detectors because of their large size and therefore the robustness to misalignment, and that the fact that that you achieve fairly good bandwidth in these systems, and the fact that if you break it down, a solar cell, they are an array of massive MIMO receivers, and trying to exploit that feature of a structure of a solar cell for MIMO operation. So here's a system you see at the bottom. We've developed 10 years ago, and we put it up on the Orkney Island in north of Scotland. There's a microwave link between the mainland of Orkney, which is that on the left upper corner, to a little island called Grahamsea, and it's a lighthouse. It's a 5-kilometer microwave link, and then we had about 50 to 800 meter point to multi-point links from the lighthouse to various houses. And you see the installation of the garage of this house here, and let the system run for over 3 months. And looked at the effect of sort of atmospheric effects, sunlight, rain, and so on. The bandwidth is fairly low of that off-the-shelf solar panel. It's just with an electrical equalizer. You got to about 8 megabit per second, and then fluctuating depending on rain, but it never really dropped to zero, which again can be attributed to the large area detector. So further work on photovoltaic cells is with the Fraunhofer ISE in Freiburg. They have gallium arsenide solar cells power converters that have very high bandwidth, and the maximum data rate we've had 8 years ago with a gallium arsenide solar cell was in the closed shortcut mode of 1 gigabit per second. So recent new work we've demonstrating with a solar cell with such a solar cell close to 4 gigabit per second. So a single cell, and then the single cells are put together into an array. You could then see how that can be used for MIMO operation. But the main principle is shown here in the circuit diagram. You have the solar cell. You have a DC output to harvest the power, and then you have a sort of a network, an equalizer to get the AC output out, and that carries the data carrying signal. And we looked at things, the impact of sunlight with a sunlight emulator. And obviously, if you have strong sunlight irradiance, the data rate goes down, the energy harvested goes up. There's always a sweet spot and a trade-off that need to be considered in doing sort of the adaptive adjustment of the operational points in a solar cell. So now moving to the indoor use case, and starting with Joe Kahn's well and famous paper where he classified the indoor deployments into line of sight, non-line of sight, directed, non-directed, and you see the 6 different modes of operation. Radio communications has been classically a non-directed, non-line of sight communication system, and is moving with millimeter wave more into the directed line of sight communication system. That's an interesting observation. At the same time, optical wireless coming from point to point, sort of IRDA kind of systems, now also moving into the non-directed, non-line of sight operation. So there's a crossing point in between, but I thought interesting to observe these different trends, which really corroborates the point that RF and optical in all the deployment scenarios I've shown work in tandem and solve the same problem in different ways and with different advantages. Now, looking into a deployment indoors, like every communication system with multiple cells, with multiple radiators that send the same signal at the same frequency, you get interference. This is shown here on the right, 2 access points with the blue squares sending signals with a field of view about 60 degrees. And you get a very nice high SNR at the center point of the transmitter, and then you get a lot of interference at the crossing points between the cones in blue. But in optical wireless, that blue interference region is very deterministic, unlike in RF communications. And if something is deterministic, you can work around that in order to resolve interference problems. But lately, we really think that in terms of dealing with the directionality of light and the non-line of sight limitations by blocking light. So one way there's 2 ways to overcome that. One is adaptive beam steering or electrical beam steering. I see Edward on the call here. Eindhoven has done great work on beam steering systems using graded sort of structures with multiple wavelengths. That's a very nice way of solving that problem. The alternative approach we've taken here is using a grid of beam approach, really extracting. So the first work on that was by Kaverat in the 1992, as you see here, the fly eye receivers, and now by extension the fly eye transmitters, really replicating the insect eye with a structure like this. You have a grid of beam in the ceiling that creates a very dense structure of attocells with these spots here, and then you see that some cells are covered. Some users are covered by a beam, a single beam, and another person in a room will be covered by a single beam. So there's no sharing of frequencies. Everyone would get their own full capacity, cell capacity, and if people move, you don't change the direction of the beam. You just switch to the other beam. So it's beam switching that would then support mobility and also support blockages. So there's a grid of beam transmitter, but also you need a grid of beam receiver, so the fly eye in the inverse region, and angular diversity receivers are sort of a method to go about that. First published by Kahn and Barry. Carruthers and Kahn in 98. So that idea is really great as well. So what we propose to do here is build sort of an array of optical concentrators, it could be lenses, it could be non-emitting lenses like CPCs here. And then to harness the full bandwidth, you wouldn't use a single detector at the output aperture. You would use an array of detectors, and assuming that the wavefront on that output is fairly homogeneous, you then can use equal gain combining at the output of the detectors. And then what you would have with a one-tier ADR, you would have seven signals that coming out of each of the aperture, and then the signals will be fairly different because of the difference of angular distribution of light that's coming in. The way to solve it in an optimum way is then use maximum ratio combiner from all the signals and then feed that into your signal processor. By this, you are able to detect then signals from various different angles and directions, giving you the robustness to move the receiver and move out of the full strict alignment region. So the downside of this of using sort of so concentrators or focusing lens is étendue. And as many of you probably will know, is that there's a relationship between the aperture size and the field of view, which is a product is constant and it never decreases. It's related to the second law of thermodynamics. So in other words, is if you want a high gain of your signal, which is the ratio between S in and S out, should be high. That means S in need to be large. But then that would mean that the omega, the field of view, omega, the input up field of view would decrease. So you get more a point-to-point receiver, and that is another argument to go into the angular diversity receiver, because you have then many narrow field of view receivers, but overall they cover a large sort of sub hemisphere. And here quickly to review why we need to have multiple detectors and detector arrays is that relationship between bandwidth and size of the detector, which is fairly well understood that the bigger the detector, the higher the capacitance, the lower the bandwidth. So you want to have very, very small detectors, but small detectors, on the other hand, require strong gain. And then with the gain limitation I've just explained earlier, you're running against some trade-offs. And the other trade-off is if you want a large gain with a CPC, that also means a large height of the concentrator. So here for 33 dB gain, for example, you would need almost the 3 centimeter height detector, which is not practical if you want to integrate it into phones. So you can resort to imaging optics like lenses, but the same principles apply there as well. And that's the trade-offs that need to be considered building the receiver. But now, really, want to finish off now quickly. So the idea is how to build that grid of beam is by using three-dimensional structures like a pyramid with an octagonal base, and we cut off the top and build an array of 25 VCSELs, a 5x5 array. On each side, you get 225 beams. The bandwidth per beam is 5 gigahertz. If you then aggregate it over the entire device, you get to data rates of above 1 terabit per second aggregate data rates, sort of system data rates. So we built the VCSEL array that you see on the right in this project Reason in the UK. You see the beam patterns that come out of these VCSELs. Some of them are Gaussian shaped, some of them are not, different modes. And that's the nature of a research chip. So the idea then is to build that full coverage with 225 cells. If you've done some modeling, output power limited to 10 milliwatt to be eye safe in the 800 or 940 nanometer. The total optical power is below 2 watt, and the aggregate data rate in simulation is above 2 terabit per second. So the problem then with all cellular systems is you get the interference between beams, as shown as the blue region here with the data rate going to 0. So it's a very, very binary sort of situation. You have 20 gigabit close, and then you move 5 centimeter and you get 0. And that's not attainable. It's not how you would be able to run the system. So to overcome that problem is by using AI and intelligent beam clustering. By when you know the location of users, you know exactly where you need to have your maximum SNR and where you can tolerate a low SNR, which is shown by the blue dashed lines here. And then you could cluster the beams in a way that the blue regions fall into the null space, into the space where there is no receiver or transmitter. And then you maximize the data rate to users and minimize interference. And if you did that with 4 different scenarios shown here as an example, you get completely different SNR maps in a room, and that is something that you can dynamically adjust to maximize the data rate. So just briefly, we have built that VXL array, and if you would like to work with us and do some experiments with an array like this, we're happy to talk to you and maybe do some joint work. But it's a 1 by 1 millimeter little VIX device that you see here with 25 outputs, 25 VXLs that can be individually addressed. And I show here with that little animation. So we activate all the 25 beams, and the problem, as you see here, is without any optics, the beams fall on the same space. So that's why we have built some nano optics around it to separate the beams. And we've started some first tests where you see that 3 beams, for example, here are already spatially separated by about 6 centimeter. So that really gets into exactly the region we want to go. 25 spatially separated beams at 3 meter covering 40 centimeter. So that brings me to the end. So really, I want to say that optical wireless communication has arrived. We see it. I see Lightworks, Archangel Lightworks, Owen on the call as well. They're doing fantastic work on ground to the satellite communications with a very, very exciting base station here in the UK. Emerging use cases. We see emerging use cases with Pure Wi-Fi indoors. We see a great deal of good work in the UK and elsewhere on optical wireless communications, and the emerging use cases are really NTN has probably taken over from the indoor. This is where there's exciting deployment of optical wireless communications underwater, and then, as I said, terabit indoor networking to allow the future world of hyper connectivity of all the autonomous systems that are coming. And lastly, I think photons, unlike electrons, which I've tried to explain earlier with the bandwidth, are inherently race cars, where electrons are very, very lazy, sort of sofa-sitting entities. But photons have been caged for too long in a fiber. So let them go out into free space and do the fast and wonderful things in free space. So that's the mission we are on, and it takes longer than we all think, but we also need to account for that we are behind the curve of RF for quite a while. So with that, thank you very much for your attention, and I hope there's still time for a few questions. Thank you.
Yes, thank you very much, Professor. I know you have a very busy agenda, so we've been certainly very lucky to have you today to be able to attend this meeting. It's always really a pleasure to be able to see you and to have you on board. You really are the rock star of optical wireless communication. It's always mind-blowing every time you do a presentation. We do have questions actually for you. And the first one is actually coming from Owen, coming from Archangel Lightworks, which I recently had the opportunity also to meet about their work and in satellite and their guide, which is really good actually because of your conclusion as well. And I will have a question to do, but first the question of Owen. Professor, what is the mean power output possible with a VXL? What is the trade-off with the bandwidth at the 1550 nanometers?
So the VXLs are not operating in the 1500 nanometers. So they are operating. The ones that we have is for 840, 960, and we've tried one over 1060 nanometers as well, which is not doing as well. Now looking at the 1300 nanometer. So the optical output power is really limited by eye safety considerations. So we have worked with a VCSEL. The solar cell system that I've shown is a 200 milliwatt off-the-shelf VCSEL we use there. For the indoor application, we limit it to 10 milliwatt. So that is the eye safety limitation that govern the data rate. And sorry, what was the question on the 1500 nanometer trade-off?
The power output and the trade-off with the bandwidth.
Um, the I mean, there's obviously a trade-off with we didn't use a 1500 nanometer sort of devices outdoors, so I can't comment on that. But if we look at the gallium nitride, the blue laser, we are working. Obviously, there's a trade-off of power and bandwidth. So currently work with one that has 6 watt optical output power at a bandwidth of above one gigahertz. Yeah, I mean, really device dependent.
Thank you very much, Professor. We do have a question also from Rahul asking about the photovoltaic cells-based communication. What are the application areas considering limited bandwidth and also the impact of strong ambient light in the outdoor? Is there any specific wavelength that responds very well for solar receiver if operating in an outdoor environment? And is there an indoor scenario where this photovoltaic cells enable communication would be useful?
Yeah. So starting with the last question, yes, there's an indoor application. If you happen to have, for example, IoT devices in your home, such as thermostats for your heaters and so on, they're typically all battery powered, and it's an inconvenient sort of situation where you have to replace and charge things. So the idea is trickle charge indoors with solar cells, and we've looked also at organic solar cells, which we are flexible. They can be bent around objects. So they can at the same time trickle charge the sort of IoT devices and act as a high-speed receiver. So that was the first question on the indoor application. Sorry, what was the question? The first
Yes.
question.
Is there any specific wavelength that responds very well for the solar receiver in an outdoor environment?
Yeah, I think they are depending on the material, right? So if you look at silicon receivers, you're talking about sort of the I think 1,000 nanometer region, which is ideal there. And if you look at the gallium arsenide, so we're looking at so 1400, 1500 nanometer VCSEL. So we really need to match technologies, and I can't comment on a particular wavelength. It's just that you need to match transmitter and receiver technologies.
Sure. Just a quick one still from Mr. Raoul. What are the application areas considering limited bandwidth for the outdoor applications? Is there any specific application
I
you're
don't
thinking
understand the
about?
question. Why is there limited bandwidth? In fact, you have a lot of bandwidth. I mean, if you look at sort of the devices, for example, ETH has done with 1 terabit per second, you talk about tens of gigahertz of bandwidth outdoors. So I don't understand why
Sure.
there's low bandwidth.
I do have a question also from Mr. Edward, talking about the network operators. One of the issues network operators are hesitating to integrate FSO into their cellular networks is the link availability.
Yeah,
Requirements for link availability is quite high, namely 5
that's right.
nines. How
That's
should
right.
we do to increase the link availability while maintaining high throughputs offered by the FSO? Another question is, are we on correct wavelengths to do FSO, or do we need to work on different wavelengths in order to suppress impact of weathers?
An extremely good question. And I say to the last question, yes. And the wavelengths out for outdoor is looked at primarily in the 1500 nanometer. And that really is my view, historic of nature because of the extension from fiber comms and the EDFAs that are working in that domain very well. But I think that's why we do the experiments here in Cambridge, looking at the visible light and gallium nitride. We want to understand better the impact of turbulence, scintillation, and so on in that region as well. As you have seen from the plot, the attenuation per kilometer in the invisible light domain is also very, very low. The impact of sunlight and irradiation is a good question as well. It is a problem if you look at pulsed modulation techniques with a strong DC component, but it is not a problem when you look at a non-DC based or modulation formats such as DC OOFDM. We've done a lot of work to show that the constant sunlight doesn't affect it. And you need to just make sure you're not saturating it. And the only additional noise that you would then incur would be shot noise. And that's why we moved also into the UVC solar blind region, because there you would also eliminate shot noise, and you would have eliminated ambient light, shot noise, and that gives you higher sensitivity levels at the receiver. So that's the hypothesis then is if you have IMDD in higher sensitivity, how well does it play when you compare it with coherent transmission at other wavelengths where you have other noise effects coming in. So yeah, I hope that answers the question around the ambient noise. Again, system designs will allow you to mitigate the effect of that.
And we do have a question also from Chuck.
So can I just Edward's comment on the availability? That is the 5 nines is a challenge and remains a challenge. Especially if fork situations are there. So the way perhaps to overcome that, and I mean, I don't have a solution, but one way to overcome is the first thing is we tried. That's why we moved into big solar panels as detectors, where if you have diffused light and you have diffused light falling on a large detector, is still light you can harness for your communication system. So that's one of the reasons why we moved into these large aperture detectors. And the other effect is if you have light, if you have fog, and you know regions where there is likelihood of good fog, is perhaps to break up the link with a multi-hop system, sort of multiple transceivers in between that are switched on when there is fog situation to break up the attenuation per link per hop. I mean, that's a more expensive solution, but one that could overcome those rare situations or situations when there is fog and weather conditions.
Thank you,
Yeah.
Professor. I do have a question also from Chuck Slivinius from Life Infinity. In the next 5 to 10 years, do you think these VCSELs will be integrated on a range of devices and equipment?
Oh yeah, I mean, I can see. I mean, they're already integrated in your phone, right? You have that for face recognition. These are commodity devices that are widespread used, and I completely see them integrated.
And the last question from Francisco Munoz. Is there any list of devices or sensor or manufacturers that can already connect via Li-Fi?
It's a question, are there Li-Fi suppliers? Or, I mean,
Are there Li-Fi ready sensor manufacturer devices? Yeah, I guess it's more about integration directly into devices, yes.
I mean, there's a number of companies that have Li-Fi devices. And one that I'm very close is Pure Li-Fi has a light antenna module that is the size of 3 by 5 millimeter. And Enrique is on the call, may be able to comment better. But there's a little device that is very integratable into phones and is Li-Fi ready. There's a Li-Fi standard. The Li-Fi such standard is described. There are Li-Fi products. Li-Fi are used in defense sectors. The Signify, Pure Li-Fi, OLEDcom, name it. European companies are delivering products. So it's all out there, and in particular use cases.
And I do have a personal question also, Professor, and probably the last question because we are already 1 minute behind the hour.
Yeah.
You were talking about Archangel, and you were talking about resilience also, and the fact that now the time for market of optical wireless communication is coming. Do you think that the latest couple of years geopolitical issues that we've seen, for example, underwater communications, GPS, satellite, and without opposing the two technologies, but with the radio frequencies being, I would say, a little bit more put outside and used and conflictual with different security, cyber security breach and sovereignty. Do you think now that all of that combined with energy problem, because we also combine that with the energy problem, do you think all of that combined would definitely help optical wireless communication becoming a new angle for a lot of countries now to look at it into a much more deeper and sovereign situation?
I'm completely convinced that this is the case. There's a very strong pull from the defense industry because of the security property of light. There's a strong pull in space communications with satellite, inter-satellite communication. There's a strong pull from satellite to ground. There's maybe not such a strong pull for indoor Wi-Fi networking, but with the applications coming with the autonomous system I've explained, there will be, in my view, strong push. And I try to highlight as well that we are still on an exponential curve in mobile data traffic production and consumption. I think that the case for Li-Fi and the case you've just explained still exists, but maybe on the slope of the curve of adoption is sort of the question: how big is that slope? I think in the next 10 years, if our predictions still are correct, we still see stronger arguments for light communication as a commercial solution.
Thank you very much, Professor. This is it for today's webinar. Thank you very much for your time. We know you're really extremely busy, and we've been really lucky to have you for this hour. It was a really interesting talk, Professor. Thank you very much for today.
Well, thank you very much for your time and everybody for joining. I hope it was worthwhile. Thank you.
Thank you for everyone for joining today's webinar. I've included the Light Communications website into the chat. If you want to stay up to date with the next coming webinar, please welcome to join the website. If you want to also join the Light Communication Alliance and to be part into more deeper communications news and information with it, our members such as the esteemed professor that's joined us today, please feel free to contact us through the website. Thank you very much for joining, and hope to see you soon on the next webinar. Thank you for everyone.
Thank you. Thank you very much.
Have a very good day. Thank you, everyone, and this will conclude today's webinar. Good morning, everyone. Thank you very much for joining today's webinar.